So now we are ready to actually get into our very first public key encryption system. So let's talk about El-Gamal encryption. This is a really clever system that was first published by the Egyptian cryptographer Tahir El-Gamal back in 1985, and it's still used today. It's highly secure, but it does have one really subtle drawback that can make it hard to implement sometimes, and we'll get into that in a later lecture. Um, but it's typically referred to as sort of just a public key system based on Diffie-Hellman, but I think there's actually a lot more to it than that. So let's get into what's going on here with El-Gamal and its relation to Diffie-Hellman. So if you recall, Diffie-Hellman key exchange cannot be used as an encryption system. Okay, so Alice or Bob cannot use Diffie-Hellman to take a message and then do some math on that and then send them ciphertext that can be decrypted. That's not what it does, because Alice and Bob have no control over what is actually created by Diffie-Hellman. The key that's created by Diffie-Hellman is almost random because it depends on Alice and Bob making two independent secret choices for X and Y. And so you can't use this to send controlled messages. You can only use this to generate a common secret key that they can then use as the key for their favorite private key or symmetric encryption system. So it's not an encryption system. It's just a way to facilitate key creation for a private key a private key encryption system. So the really smart thing about El-Gamal is that it uses the randomness that's involved in Diffie-Hellman key creation, which was, of course, designed to facilitate symmetric systems, and instead it uses it to create a brand new public key encryption system. So it's really clever. And the point to remember through this entire write-up here is that El-Gamal is a public key system. And all it is simply a mashup of Diffie-Hellman key exchange layered on top of an affine cipher. And so you already understand Diffie-Hellman key exchange, and you certainly already understand affine ciphers. So you already know all this. We just got to put it together and understand how El-Gamal operates. So let's do it. There's only one piece of math that you need in order to understand this. So because this is going to be inspired by Diffie-Hellman, we're going to work modulo a prime p, just as you would in Diffie-Hellman. And we're also, at some point, we're going to have a primitive element floating around for exactly the same reasons as we did in Diffie-Hellman. And so here's the fundamental math question we need to settle before we go any further. Which elements mod p are actually invertible? Okay, that's the question we need to answer. So let's look at an example of this. Let's take a really small prime that we can just play with very easily. Let's work mod 5, okay? So if you work mod 5, your entire universe just consists of the numbers 0, 1, 2, 3, and 4, right? That's all you have when you work mod 5 is 0, 1, 2, 3, and 4. So the question is which of these 5 elements are actually invertible? Now, of course, 0 is not invertible. It never is. But you can check that every other element actually is invertible. You can check that 1 and 4 are their own inverses, and 2 and 3 are each other's inverses, right? 2 times 3 is 6, but 6 is 1, right? And so 2 and 3 form an inverse pair. So when you work mod 5, everybody's invertible except for 0, right? And 0 could never be invertible anyway. So when you work mod 5, you have 4 invertible elements, everybody except 0. And you should consider this as the best case scenario, because if you have 5 things and one of them is never, ever, ever going to be invertible, the best case scenario is that the other 4 are. And that's what is so nice about primes, okay? So you already know this, by the way, and you're not at all surprised, and it's because you know so much about Euler's phi function, right? You know that phi of p would count the number of invertible elements mod p, but when p is a prime, phi of p is p minus 1, right? And what that says is if you're working mod p, everybody except for 1 is invertible, and that one person is, of course, 0. So you already knew all this. And so this is the important fact that we need to understand why El-Gamal works. Let p be a prime. When you work mod p, all the non-zero elements are invertible. Okay, so in other words, the only element mod p that fails to be invertible is 0, which of course is always going to fail. So this is what we care about. Okay, that's why primes are special. Okay, so recall what Diffie-Hellman does, right? Diffie-Hellman creates a key, but it creates a key from the list 1, 2, 3, up to p minus 1, right? Well, wait a minute. That means that Diffie-Hellman creates an element mod p except for 0, right? Diffie-Hellman creates a non-zero element mod p. So that means that Diffie-Hellman necessarily manufactures an invertible element mod p. So when you do Diffie-Hellman, what you get is a non-zero element mod p. So what you get is someone that has to be invertible. And the point is, well, that invertible element mod p could now be used as the multiplicative part of an affine cipher, right? In an affine cipher mod p, you need the multiplicative key to be invertible. Well, Diffie-Hellman will manufacture that for you. And we can just take 0 as the additive key. We're just going to throw the additive part away. And this is why El-Gamal works, okay? That's the whole story pretty much. So here is El-Gamal in a nutshell. What you do is you use Diffie-Hellman key exchange to create an invertible element k mod p. And then you use that multiplicative as the multiplicative key for an affine cipher. So you encrypt a message x by the encryption of x will be k times x mod p, right? So this is just the affine cipher k times x plus 0. And this is, of course, a valid affine cipher because k is invertible. That's El-Gamal, okay? Now we got to talk about how this works for public key encryption. It's not exactly obvious, and then how you actually use this, and then in a later lecture we're going to examine the security of this. Why is this secure? Okay, so if you just think about this a bit, it's probably a good idea, because what you're going to see is that we are never going to have to transmit the key k over the open line. So this is kind of a miracle. You're going to be able to do this affine encryption, but never need to transmit the multiplicative key over the channel. You never need to. Right? Now, the only real weakness we've seen in an affine cipher comes from the vulnerabilities of English language, right? When I work modulo a giant P, this won't be brute forceable, right? There's going to be way too many keys. It'll be P minus 1 different keys that could happen. And if P is, 18 trillion, well, then P minus 1 is also very close to 18 trillion, so you can't brute force it. But there are, of course, vulnerabilities and patterns in your plain text, but El-Gamal is only used on large numerical random data, so it's not going to matter here. There won't be any patterns, so we're actually going to be fine, okay? So let's talk about sort of what the public key data would look like here if you want to do this, and then we'll take a break, and then we'll come back and actually do the protocol. So El-Gamal is going to be a public key system, and so that means that every user, remember this, will have their own individualized key data, right? You don't have Alice and Bob sharing a key, agreeing on a key ahead of time. No. Alice has her own key, and then separate from that, Bob has his own key, right? So here's how Alice establishes her El-Gamal key data. She first chooses a very large prime P, and she also chooses a primitive element G mod P. That should sound familiar. That should sound like Diffie-Hellman, okay? Next, she chooses a positive integer x in secret, okay? That x is going to be secret. And she uses this to calculate A, which is going to be G to the X mod P, but she doesn't tell anybody how she's computing this, okay? That's done behind closed doors. Does that sound familiar too? Yes, that's Diffie-Hellman. So this is so far exactly Diffie-Hellman. And then Alice publishes the data P, G, and A as being public, okay? So her public key data is the prime P, the primitive element G, and the value of A, but notice that she is not divulging what X is. X is going to be her private decryption key, okay? So far, all right, this is exactly the first half of a Diffie-Hellman key exchange, okay? The only difference is that Bob is going to have his own three-part data, a different prime, a different primitive, and a different value of what would be B here. So everyone's going to have different values, okay? So this is where where El-Gamal starts to diverge from how Diffie-Hellman behaves. So let's take a break here, and we'll come back and talk about what a message is and how Bob would encrypt a message to send it to Alice and how she would decrypt it.